There is a question that has lived quietly inside human beings for longer than recorded history can reach. It rises naturally on clear nights when the darkness above seems to go on forever. It arrives uninvited during moments of stillness, when the ordinary noise of daily life recedes long enough for something deeper to surface. And it is a question so simple, so clean in its construction, that a child can ask it without stumbling over the words. Are we alone? Not alone in the way a person feels alone in a crowd. Not alone in the way a traveler feels far from home. Alone in the most absolute, most permanent, most cosmically final sense imaginable. Alone as in, of all the stars scattered across a universe so vast that our finest instruments have not yet found its edges. Not one of them shelters another mind looking back at us. That question deserves to be taken seriously, and yet for most of human history, it was handed over to philosophers and poets and dreamers, as if its answer were simply a matter of opinion, or preference, or faith. It was not treated as something science could address. It was not thought of as a problem with discoverable constraints and measurable parameters. It was just there, hovering above us, beautiful and unanswerable, and perhaps best left alone. That changed in the summer of 1950. And the strange thing is, it changed because of a single remark made over lunch by a man who was not even thinking about alien life at the time. The physicist Enrico Fermi was walking to the cafeteria at Los Alamos with a group of colleagues. The conversation was light. A cartoon in a magazine, something about a recent wave of UFO sightings, nothing particularly serious. They sat down to eat. The discussion moved on to other things, and then, after a pause, Fermi looked up from his meal and asked a question that has never fully stopped echoing. Where is everybody? Those three words have since become one of the most examined, most debated, most unsettling observations in the history of scientific thought, because buried inside that simple question is a contradiction so deep and so persistent that decades of searching, theorizing, calculating, and listening have not been able to dissolve it. The universe is extraordinarily old. It has existed for approximately 13.5 billion years, a span of time so enormous that our entire planet, with its long procession of ice ages and extinctions and evolutionary experiments, occupies only the final third of it. Stars had already lived and died for billions of years before our sun ignited. Galaxies had already formed, matured, and evolved before Earth existed as anything more than a swirling cloud of gas and dust. And the universe is not just old. It is incomprehensibly large, populated with hundreds of billions of galaxies, each containing hundreds of billions of stars. The raw numbers suggest that the conditions for life, whatever those conditions precisely are, should have had countless opportunities to occur. The mathematics of sheer probability seems to scream that we cannot possibly be the only ones. And yet, we have listened carefully to the sky for decades now. We have aimed our most sensitive instruments at thousands of stars. We have scanned frequencies that by reasonable logic, an intelligent civilization might use to announce itself. We have searched for laser pulses, for unusual heat signatures, for patterns in starlight that natural processes cannot easily explain. We have extended our search in recent years to examine entire galaxies for signs of engineering on a civilizational scale. We have found nothing, not a whisper, not a faint, ambiguous signal that might be something. not a tantalizing anomaly that keeps scientists arguing late into the night. Nothing that has withstood scrutiny, nothing that has held up. A silence so complete, so uniform, so stubborn across every frequency and every direction that it demands explanation. This is the Fermi Paradox, not really a paradox in the strict logical sense, but a profound mismatch between expectation and reality, between what the numbers seem to promise and what the universe has actually delivered, and the explanations that have been offered over the years. Some of them reasonable, some of them disturbing, some of them so strange they feel more like science fiction than science, form a kind of map of our own deepest anxieties about what it means to be a thinking species in a universe that may have no interest in thinking back. The story of why we may never meet another civilization is not really a story about space, not fundamentally. It is a story about what life is, how rare complexity might be, how fragile intelligence turns out to be, and what a universe that permits consciousness but does not celebrate it might actually look like. To understand it, we have to start not with the silence, but with the optimism that made the silence so surprising. In 1961, a young astronomer named Frank Drake sat down with a piece of paper and wrote out an equation. He was preparing for what would become the first serious scientific conference on the search for extraterrestrial intelligence. And he wanted a framework, a way of organizing the question, of breaking it into its component parts, so that the problem could be approached systematically rather than emotionally. The equation he wrote was deceptively elegant. It began with a question about how many stars form in our galaxy each year. It moved through what fraction of those stars have planets, then to what fraction of those planets might be capable of supporting life, then to what fraction of those worlds actually develop life, then to what fraction of living worlds eventually produce intelligence, then to what fraction of intelligent species develop the technology to communicate across space,
cosmos,
and finally, to the crucial and most uncertain variable of all, how long such a civilization survives before it falls silent, either through catastrophe, or transcendence, or simple change. Multiply these factors together, and the result is an estimate of how many civilizations might currently exist in our galaxy, and be willing and able to make contact. Drake and his colleagues, gathering in Green Bank, West Virginia, found that when they plugged in reasonable estimates for each factor, the equation produced numbers that were, by almost any measure, encouraging. Perhaps tens of thousands of civilizations, perhaps millions. The galaxy, it seemed, should be teeming. That optimism was not naive. It was grounded in a genuine scientific logic. Life, after all, is chemistry. And chemistry operates according to universal laws that do not change from one star system to the next. The carbon that makes up every living thing on Earth was forged in stellar cores across the galaxy. The water that fills our oceans follows the same molecular rules everywhere in the cosmos. If the conditions are right, a rocky planet at the right distance from a stable star, liquid water on the surface, the right chemical building blocks, then life, the thinking went, should emerge the way crystals grow or rivers find their paths to the sea, inevitably, almost mechanically, as a natural consequence of chemistry, given enough time and the right environment. And planets, it turned out, are not rare at all. This was perhaps the most dramatic discovery of the past 3 decades. When astronomers finally developed the tools to detect worlds orbiting other stars, using the tiny dips in starlight as a planet passes in front of its sun, or the subtle gravitational tug a planet exerts on the star it orbits. They found planets everywhere, around almost every star they examined, around stars that burn hotter than our sun and stars that burn cooler, around stars that are twice as old as the Earth and stars that formed only recently by cosmic standards, around binary stars, stars in clusters, stars in the outskirts of the galaxy and stars near its center. The planet count in our galaxy alone now stands in the hundreds of billions. And among those hundreds of billions, astronomers have identified thousands that sit within what they call the habitable zone, the orbital range where a planet receives enough stellar warmth to potentially maintain liquid water on its surface, not too hot, not too cold.
Of the cosmos,
the temperature range that
the
on
Milky
Earth turned a ball of rock
fades
into a living world, all of which
inviting
makes the
us
silence even harder to explain. Because here is the thing about the universe's age. Here is the piece of this puzzle that Fermi grasped immediately over that cafeteria lunch. Even if civilizations are relatively rare, even if only one star in a million ever gives rise to an intelligent species, in a galaxy that has been forming stars for 10 billion years, there have been billions of opportunities. A civilization that emerged even a billion years before us would have had time to spread across the galaxy many times over, even at speeds far below the speed of light. A species that began exploring the stars 100 million years ago, at a pace we would consider leisurely, would have visited every corner of the Milky Way long before our ancestors were recognizable as primates. The galaxy is old enough and large enough that any civilization with the drive to expand should have left marks everywhere. And yet we see none. That is the paradox, not the absence of a radio signal, the absence of everything. Before we explore what that silence might mean, it is worth pausing for a moment to appreciate just how carefully we have listened. The first serious attempt to detect a radio signal from another civilization was made in 1960 by Frank Drake himself. Using a radio telescope in West Virginia, he called the project Ozma, named after the princess of a fictional far land, and for about 200 hours he pointed the telescope at two nearby sun-like stars. Listening at a specific frequency, he heard nothing unusual. What followed over the next 6 decades was a slow, patient, and increasingly sophisticated expansion of that search. Radio telescopes grew larger. Signal processing became faster. The range of frequencies explored broadened. The number of stars examined grew from a handful to 1,000 to millions. Optical searches were added, looking for laser pulses that an advanced civilization might use to communicate. Later, scientists began examining the infrared signatures of entire galaxies, looking for the waste heat that a civilization using the energy of millions of stars would inevitably produce. The most famous moment in this long search came on August 15, 1977, when an astronomer named Jerry Emmon was reviewing data from the Big Ear Radio Telescope in Ohio. He came across a signal unlike anything in the surrounding noise, a narrow-band transmission that peaked briefly at exactly the frequency hydrogen emits in space, the frequency many researchers considered the most logical choice for an interstellar beacon. The signal lasted for 72 seconds, the maximum window the telescope's rotation allowed, and then it was gone. Emmon circled it in the printout and wrote a single word in the margin. Wow. That annotation gave the signal its name, and the wow signal has remained one of the most tantalizing and frustrating events in the history of research. It has never been detected again, despite many attempts with more powerful equipment. Its origin remains officially unexplained, though most researchers today consider a natural or human-made source more likely than an alien transmission. The signal left no sequel. It offered no confirmation. It remains suspended in that particular category of things. Not explained, not dismissed, not resolved. Everything else has fallen into the second category. Explained: satellite interference, interstellar hydrogen clouds, rotating neutron stars, gravitational lensing effects, natural processes that mimic, in some superficial way, the patterns we might expect from an intelligent source. The silence is real. It is not an artifact of limited searching. It is a feature of the universe as we have so far encountered it, and the explanations that attempt to account for it fall into three very different types, each with its own implications, each with its own particular shade of unease. The first type of explanation asks a simple question. What if the Drake equation is fundamentally more pessimistic than it looks? What if one or more of its factors, those carefully estimated probabilities, is not 1 in 1,000 or 1 in a million, but something so small it makes the eventual product of the equation essentially zero? What if we are, against all mathematical intuition, effectively alone? This is the position sometimes called the rare Earth hypothesis, developed in detail by the paleontologist Peter Ward and the astronomer Joe Kirschvink, among others. It does not argue that life is impossible elsewhere. It argues that the particular chain of conditions required for complex, intelligent life, the kind that builds radio telescopes and asks questions about the universe, is so precisely specific, so dependent on a sequence of events that almost did not happen, that its occurrence might be extraordinarily rare. Consider what had to be true for Earth to become the world it is. Our Sun is a relatively stable, middle-aged star, not the most common type in the galaxy. Red dwarf stars, which are smaller and dimmer and much more temperamental, make up roughly 3/4 of all stars. The Earth sits in its habitable zone at just the right distance. But distance alone is not enough. The Earth has a large moon, formed in a violent collision early in the solar system's history. That moon stabilizes Earth's axial tilt, keeping our seasons relatively predictable over millions of years, and preventing the kind of chaotic wobble that might otherwise make the climate too unstable for complex life to evolve. Without the moon, Earth's tilt might swing wildly over geological timescales, producing climate shifts too rapid for evolution to track. Jupiter, the massive gas giant that sits further out in the solar system, acts as a gravitational shield. Its enormous gravity deflects or captures many of the comets and asteroids that would otherwise bombard the inner solar system with devastating frequency. Life on Earth has been interrupted by major impacts before, but the rate of those impacts might be far higher without Jupiter's protective influence. Earth has a magnetic field generated by the motion of molten iron in its core that shields the surface from the most energetic particles streaming from the sun. Without that field, the solar wind would erode the atmosphere over millions of years, as it did on Mars, stripping away the blanket of gas that keeps the oceans liquid and the surface habitable. Plate tectonics, the slow grinding movement of the continents across the surface, recycles carbon, regulates the planet's temperature over long timescales, and creates the geological diversity that drives evolution. Not all rocky planets have plate tectonics. What determines whether a world develops it is still not fully understood. Earth has it, Mars does not. Each of these factors, taken alone, might seem like a detail. Together, they suggest something more troubling. The probability that all of them occur simultaneously on the same world might be genuinely small, and that is before we even get to the biological questions. The probability that life arises from chemistry in the first place, that it transitions from simple cellular life to complex multicellular organisms, that it eventually produces a species with the cognitive capacity to understand the universe it inhabits. The history of life on Earth is instructive here, and not entirely in the direction of optimism. Life appeared relatively quickly after Earth formed. Within the first few 100 million years, as soon as conditions allowed, simple microbial life seems, by this evidence, not especially difficult to produce. Chemistry, given the right conditions, and enough time apparently finds a way. But the transition from simple life to complex life is a different story. For roughly the first 2 billion years of life on Earth, nothing more complex than single-celled organisms existed. The emergence of the eukaryotic cell, the type of cell with a nucleus from which all complex life descends, appears to have been a singular event, a fusion of two different types of bacteria, so improbable that it may have happened only once in the entire history of this planet. Not once per million years. Once, the evolutionary biologist Ernst Mayr estimated that the path from single-celled life to a species capable of developing technology was so dependent on contingent historical accidents that if you could rewind Earth's history and run the tape again, the outcome would almost certainly be different. Not just somewhat different, radically different. A world full of bacteria and algae, perhaps, but nothing that builds cities or aims radio telescopes at the stars. If that is true, if the emergence of intelligence is not an inevitable destination that evolution reliably finds, but an extraordinary improbability that happened here through a long chain of accidents, then the silence begins to make a different kind of sense. Not a terrifying sense, just a lonely one. We might be a fluke, a statistical miracle, a universe that produced one species capable of asking where everyone else is. And the answer is that there is no one else, because the conditions that produced us were too specific, too fragile, too dependent on an improbable sequence of events to have been replicated elsewhere. The universe would not be cruel in that scenario. It would simply be vast and empty, in the way that a shoreline is mostly water. The fact that land exists does not mean it should be everywhere. But that explanation, though it has its defenders, sits uncomfortably with what we now know about the abundance of planets and the chemistry of life. It requires us to believe that something we see happening around us continuously, the self-organization of chemistry into complexity, failed to produce anything like us anywhere else in a galaxy of hundreds of billions of stars over 10 billion years. That seems like a lot to accept. And so the second category of explanations points in a different direction. What if life is not as rare as the rare Earth hypothesis suggests? What if microbial life, at least, is relatively common across the galaxy? What if the silence does not come from the rarity of origins, but from something that happens later? Something that prevents complex, communicating civilizations from persisting long enough to be heard? This is the great filter. And it is perhaps the most philosophically unsettling idea in this entire discussion. The Great Filter was proposed by economist Robin Hanson in 1998. It is not an explanation for the silence on its own. It is a framework for thinking about where, in the long journey from inert chemistry to spacefaring civilization, the journey most often ends. Think of the path from a rocky, water-bearing planet to a civilization sending signals across the galaxy as a series of steps, each with its own probability of being successfully crossed. Origin of self-replicating chemistry, emergence of the eukaryotic cell, multicellular life, complex animal life, intelligence, technology, sustained civilization, interstellar presence, the fact that we observe silence, the fact that the galaxy appears empty of technological civilizations, means that somewhere in this sequence there is a filter, something that almost everything fails to cross, something that stops the progression repeatedly, reliably, everywhere. The Great Filter must exist somewhere. The question is where. If it lies behind us, if it has already been crossed, then humanity's existence on the far side of it is something to be grateful for. Perhaps the filter is the origin of life itself, so difficult that it happened only here and perhaps nowhere else. Perhaps it is the emergence of the eukaryotic cell. Perhaps it is the development of complex brains. Whatever it is, if it is behind us, then we are already the rare, lucky exception. We have passed through the bottleneck. What lies ahead may be open, if difficult, but if the Great Filter lies ahead of us, if it is something that technological civilizations routinely encounter and fail to survive, then the silence takes on a very different and far more disturbing character. Every time a civilization reaches the stage of development we are at right now, capable of traveling beyond its home world, capable of communicating across space, capable of affecting the chemistry of its own atmosphere on a planetary scale, something happens. And whatever happens, it happens consistently enough to explain why the galaxy remains quiet. In that scenario, our development of radio communication and nuclear weapons, and the technological capacity to alter the climate of our own planet, is not a sign of exceptional success. It is the threshold at which civilizations tend to disappear. The most obvious candidates for an ahead-lying Great Filter are not difficult to imagine, because we have already invented most of them. Nuclear weapons, engineered biological agents, the destabilization of a planet's climate through unchecked industrial activity, the emergence of artificial intelligence systems that pursue objectives misaligned with the survival of their creators, the development of nanotechnology that escapes control. A civilization does not need to deploy these things deliberately to be destroyed by them. It only needs to develop them without developing, at the same time, the wisdom, the coordination, and the institutional resilience to manage them. And the history of our own species provides no particular reason for confidence that these qualities arrive automatically alongside technological capability. What is especially unnerving about the Great Filter hypothesis is what it implies about the detection of life elsewhere. If the filter lies ahead, then finding evidence of simple microbial life on Mars, or in the oceans of Europa, or in the atmosphere of a distant exoplanet would not be good news. It would be, in a very specific sense, a warning. It would mean that the origin of life is not the filter. It would mean the filter is something that comes after. And if the filter is ahead of us, finding that life got started elsewhere is a sign that we are approaching something that has stopped everyone who came before. That is a strange and sobering thought. The discovery of a fossilized microbe on Mars would be one of the greatest moments in the history of science. It would also be, if the great filter logic is correct, evidence that the sky is quiet for reasons that should concern us deeply. There is a third category of explanation. It is more speculative in some ways, but it is worth taking seriously because it does not require life to be rare or civilizations to destroy themselves. It simply requires the universe to be different from what we have assumed. What if advanced civilizations exist? Many of them, perhaps. But they are simply not doing what we expected them to do. We have been listening for radio signals because we use radio signals. We have looked for laser pulses because we use lasers. We have assumed that an advanced civilization would want to announce itself to the galaxy, or at minimum, that it would produce detectable signatures as a byproduct of its ordinary activities. But these assumptions are grounded in our own very brief technological history. We have been capable of transmitting radio waves into space for about 100 years. In the vastness of cosmic time, that is a single moment, and it is not entirely clear that radio broadcasting is a technology any civilization uses for more than a brief window, before transitioning to something more efficient, more directed, more contained. Think about the trajectory of our own communications technology. A century ago, powerful AM radio stations were broadcasting enormous amounts of energy into the sky, a beacon that any sufficiently sensitive receiver at a nearby star could potentially detect. Today, our communications increasingly happen through fiber optic cables, through highly directed satellite links, through compressed digital signals that are far harder to detect at a distance. We are not becoming quieter because we are hiding. We are becoming quieter because directed communication is more efficient than broadcasting, and efficiency is a universal pressure that any civilization with limited energy resources will eventually face. A civilization that has existed for 1,000,000 years, let alone 1,000,000,000, would look nothing like us. Its communication technologies would be as far beyond our radio telescopes as our smartphones are beyond smoke signals, and the signals it uses might be entirely invisible to us. Not because they are hidden, but because we lack the conceptual and technological framework to recognize them. This is sometimes called the zoo hypothesis in its more extreme forms. The idea that advanced civilizations are aware of us, but have chosen not to interfere, watching from a distance the way biologists observe an ecosystem without disturbing it. Or the dark forest hypothesis, drawn from a novel by the Chinese science fiction author Liu Cixin, which proposes that the silence is not peaceful but strategic. That in a universe where resources are finite and intentions are unverifiable, civilizations that announce their presence risk attracting civilizations that will destroy them before they can pose a threat. And so every civilization that survives learns quickly to stay quiet. These ideas are difficult to test. They are not falsifiable in the way a good scientific hypothesis should be, but they point to something real. Our search has been shaped by assumptions about what advanced intelligence does. And those assumptions may be wrong in ways we cannot currently identify. There is something else to consider here, something that tends to get overlooked in discussions of the Fermi Paradox, because it is uncomfortable and runs against our instinct to imagine that alien minds, however different they might be in biology or appearance, would share something like our drive toward expansion and communication. Intelligence, as we understand it, is not one thing. It is a collection of capacities that happen to evolve together on one planet, in one lineage, over a few 100,000 years. Our curiosity about the universe, our drive to explore, our desire to communicate. These are features of human psychology, shaped by specific evolutionary pressures on a specific world. They are not requirements for intelligence in the abstract. An alien mind might be intelligent in ways that are genuinely foreign to us, capable of solving complex problems, capable of modifying its environment, perhaps capable of feats of cognition we cannot imagine, without possessing any of the particular drives that lead us to build telescopes and broadcast our existence into the cosmos. It might be intelligent without being curious. It might be curious without being communicative. It might be communicative without caring about other species. We have been listening for minds that think like us. But the universe is not obligated to produce minds that think like us. Each of these explanations, the rare earth, the great filter, the silence of difference, carries something within it that resists easy comfort. The rare earth says we might be a lonely miracle in a vast and mostly empty universe. That loneliness is not tragedy in the conventional sense, but it is a particular kind of weight. To look up at a sky full of 100 billion galaxies and understand that in all of that, the only voices are our own. That is an awareness that changes something. The great filter says that if life is common, then civilizations routinely reach a point beyond which they do not survive. That point may or may not lie ahead of us. But if it does, then our current moment, with all its technological capability and all its unresolved tensions about how to manage that capability, is not a story of progress, but a story in progress, and progress is not guaranteed. The silence of difference says, we may be looking for the wrong things in the wrong ways, and that the universe could be full of intelligence that we cannot recognize, cannot reach, and cannot communicate with in any meaningful time frame. None of these is comforting in the simple way that the discovery of a neighboring civilization would be comforting. None of them resolves the question. They reframe it, deepen it, and in doing so, make it more demanding of us. There is one more piece of this that needs to be examined before we can go further, because it concerns not just whether civilizations exist elsewhere, but whether they could plausibly reach each other, even if they do. The distances involved in interstellar travel are not merely large. They are of a different category from anything human beings have direct experience with. Our nearest stellar neighbor, Proxima Centauri, sits at a distance of approximately 4.24 light-years from our Sun. In the unit we most naturally use for space travel, the kilometer, that distance is approximately 40 trillion. Every rocket we have ever launched, every spacecraft that has ever left our planet, travels at a small fraction of the speed of light. Voyager 1, our most distant human-made object, has been traveling for nearly half a century and has covered roughly 23 billion kilometers, not even 0.1% of the distance to the nearest star. At the speed of our fastest current spacecraft, reaching Proxima Centauri would take approximately 75,000 years. This is not a temporary technological limitation that clever engineering will soon overcome. The energy required to accelerate even a modest payload to a significant fraction of the speed of light, fast enough to reach another star within a human lifetime, is extraordinary by any standard. The problems of radiation exposure, fuel mass, propulsion, and structural integrity at high velocities are not unsolved details. They are fundamental constraints imposed by physics, This does not mean interstellar travel is impossible. Over very long timescales, with very different technologies than we currently possess, it may be achievable. Theoretical proposals exist. Laser-driven light sails, nuclear pulse propulsion, antimatter drives, each of which could, in principle, reduce interstellar travel times from tens of thousands of years to decades or centuries. But consider what this means for the Fermi Paradox. Even if a civilization developed the ability to travel between stars, the process of colonizing a galaxy is slow on human timescales. A civilization that expands at 1% of the speed of light, an enormous achievement, would need tens of millions of years to fill the Milky Way. That sounds like a long time. On geological timescales, it is not. Our galaxy has existed for over 10 billion years, and yet nothing. No traces, no megastructures detectable around nearby stars, no artifacts, no visitors, no signals that have held up to scrutiny. The distances are real. The energy costs are real, but they do not by themselves explain a silence this complete. It is worth spending a moment with a concept that rarely makes it into casual discussions of the Fermi Paradox, but that may, in the end, be one of the most important ideas in this entire inquiry. We tend to think of the search for extraterrestrial intelligence as a search across space. We point our telescopes at distant stars and listen for transmissions that might have crossed the void between solar systems. But the search is also necessarily a search across time. The universe is 13.8 billion years old. The Milky Way has been forming stars for most of that time. If civilizations are scattered across the galaxy, they are almost certainly not all at the same stage of development. They are separated not just by light years, but by millions of years of evolutionary and technological history. A civilization that emerged a billion years before us would, if it still exists, be so far beyond our current state that we might not recognize it as a civilization at all. Its technology would be indistinguishable from natural processes, in the same way that a medieval European, encountering a modern smartphone, might conclude it was magic. Such a civilization might have restructured itself in ways that are entirely invisible to our current instruments. It might exist in forms, uploading minds into computational substrates, dwelling in artificial environments, operating at scales we cannot perceive, that leave no signature we know how to look for. Conversely, a civilization that emerges a billion years after us has not yet appeared. The stars that will one day warm its home planet may not yet exist. The chemical processes that will eventually produce it are perhaps just now beginning in some nascent solar system, too early by far for any signature to have reached us. The window in which two civilizations need to exist simultaneously, be close enough to each other to detect, and be using technologies compatible enough to recognize. That window is not large. The universe is old and the galaxy is large, and the timing problem alone makes contact between civilizations a far more difficult proposition than the raw numbers of stars and planets initially suggest. We are not just looking for civilizations in space. We are looking for civilizations that happen to exist right now, in our cosmic moment, within the range of our instruments, using technologies we recognize, in a state of development where they are both able and willing to be found. That is a much more constrained search than it first appears. Let us pull back slightly and look at this from a different angle, not from the perspective of the astronomer with the radio telescope, but from the perspective of what Earth's own history might tell us about the probability of producing a communicating civilization. Earth is approximately 4.5 billion years old. Life appeared within the first billion years. But for the next 2 billion years, roughly half of Earth's entire history, life remained resolutely simple, single-celled, microscopic, patient in ways that have nothing to do with patience, because patience requires awareness, and awareness was not yet on the table. The emergence of complex, multicellular life required a change in the atmosphere. For the first half of Earth's history, there was no significant oxygen in the air. Oxygen is produced by photosynthesis, and photosynthesis requires particular organisms that took a long time to appear and spread. When they did, the oxygen they produced was initially toxic to most of the life that existed. There was a mass die-off, what scientists call the Great Oxidation Event, followed eventually by the emergence of organisms that could use this new chemical as fuel. The history of complex life is, in a sense, the history of learning to breathe a poison. Even after complex life appeared, the road to intelligence was not direct. Multicellular life existed for hundreds of millions of years before anything resembling a nervous system appeared. Nervous systems existed for hundreds of millions of years before anything resembling a brain capable of abstract thought appeared. And abstract thought existed, in some form, in various lineages of animals for millions of years before one particular species figured out how to record information outside of biological memory, build cumulative technology, and eventually point metal dishes at the sky and listen for other minds. None of this was inevitable. The asteroid that struck Earth 66 million years ago and ended the reign of the non-avian dinosaurs was not a scheduled event. It was a random trajectory intersection. Had it missed, the subsequent 66 million years of mammalian evolution, which eventually produced us, would not have happened. Mammals were small, nocturnal, ecologically minor creatures before that impact cleared the space that allowed them to diversify and expand. The evolutionary conditions that eventually produced large-brained primates depended on a collision with a rock that had nothing whatsoever to do with the eventual outcome. How many of those contingent, improbable steps have to be counted before we can say confidently that the emergence of a civilization like ours on another world is merely a matter of waiting long enough for the numbers to work out? And yet, and this is the tension that never quite resolves, we know that the basic chemistry of life is not exotic. We know that amino acids form in interstellar space without any help from biology. We know that the building blocks of RNA can assemble in conditions that might plausibly exist on many worlds. We know that life on Earth, once it appeared, proved extraordinarily tenacious. Surviving ice ages that covered the entire planet, mass extinctions, drastic shifts in atmospheric chemistry, and impacts that reshaped the surface. Life, in its simplest forms, appears to want to exist. The question that haunts the Fermi Paradox is whether that wanting extends to the kind of life that can eventually wonder about its own existence. There is something that has not yet been said in this exploration, something that tends to be avoided because it is uncomfortable in a specific way. Not the discomfort of fear, but the discomfort of genuine uncertainty about our own place in the hierarchy of what is possible. When we search for extraterrestrial intelligence, we are implicitly assuming that intelligence of a recognizable kind, minds that communicate, that build, that explore, is the natural culmination of biological evolution, something that complex life tends toward the way rivers tend toward the sea. We are assuming, in other words, that we are not a peculiarity but a destination. There is no particular reason to believe this. Our own evolutionary history suggests that intelligence, in the human sense, appeared once in a lineage of animals that was, for most of its history, not especially remarkable. Other lineages produced different solutions to the problems of survival. Octopuses developed distributed nervous systems and remarkable problem-solving abilities along a completely different evolutionary pathway. Corvids, crows, ravens, jays, demonstrate cognitive flexibility and tool use that astonishes researchers. Elephants show evidence of self-awareness. Dolphins communicate in complex ways that remain poorly understood. But none of these lineages is building radio telescopes. The combination of cognitive capacity, social structure, manipulative appendages, long developmental period with extensive learning, and particular ecological pressures that resulted in technological civilization appears to have happened once on this planet. It is not obvious that it should happen readily anywhere else. And there is a deeper uncertainty beneath this one. We tend to assume that a technologically capable species would inevitably turn some portion of its attention to the question of other civilizations. That curiosity about the universe would be a natural feature of any mind powerful enough to develop space travel. That the desire to communicate would be as universal as the capacity to think. But this assumption is rooted in the specific psychology of one species on one planet. There is no guarantee that intelligence anywhere else would come packaged with our particular brand of outward-reaching curiosity. A civilization might be entirely turned inward, absorbed in the richness of its own internal experience, indifferent to whatever might exist beyond its own world. It might communicate, but only among itself, in modes that leave no trace we can detect. It might develop technology without developing the particular ambition to reach other stars or broadcast its existence into the void. We are looking for minds that want to be found. The universe may contain minds that do not. All of these threads, the mathematics of probability, the history of Earth, the physics of distance, the nature of intelligence, the timing problem, the possibility of self-destruction, weave together into something that resists a clean resolution. There is no single answer to the Fermi Paradox. There may never be. And that in itself is revealing. We have been asking the question for the better part of a century with increasing scientific rigor, and the honest answer is that we do not know whether we are alone or not. We have not found anyone. We have not proven there is no one to find. We sit in an uncertain middle, listening carefully to a universe that so far has not answered. What we can say with confidence is this: the silence is real. It is not the result of insufficient searching, though more searching is always warranted. It is a genuine feature of our observations, and the explanations that might account for it range from the merely humbling. We are rare to the deeply sobering. Something tends to stop civilizations before they can reach each other, and threaded through all of these is the question that Fermi's offhand remark at lunch quietly introduced into scientific culture. The question that has never been fully put down. Where is everybody? The fact that we cannot answer it is not a failure of science. It is a reflection of the genuine strangeness of our situation. We are a species that has existed for a cosmically insignificant moment, on a planet that has existed for less than a third of the universe's history, in a galaxy that contains hundreds of billions of stars, asking whether we are alone. The audacity of the question is itself remarkable. The silence that greets it may be remarkable too, in ways we have not yet fully learned to read. There is a number that astronomers sometimes mention in discussions of the Fermi Paradox, and it tends to produce a particular kind of silence in the room when it is introduced. Not the dramatic silence of a revelation, but the quieter silence of a thought that needs a moment to settle. The number is one. One confirmed example of life in the universe. One planet out of all the hundreds of billions we now know to exist, where chemistry arranged itself into something that breathes and grows and eventually thinks. One data point, a single measurement from which we are attempting to draw conclusions about a universe that contains more stars than there are grains of sand on every beach on Earth. The scientific name for this problem is the problem of a sample size of 1, and it cuts to the heart of every confident statement anyone has ever made about the likelihood of life elsewhere. When statisticians want to know whether a coin is fair, they flip it many times. When biologists want to understand whether a drug works, they test it on many patients. When geologists want to understand plate tectonics, they can study multiple tectonic plates on multiple continents. The knowledge we have built about the natural world is almost always grounded in repeated observations, in patterns that hold across many instances, in the security of knowing that what we see is not an accident of having looked only once. We have looked only once. Everything we know about the origin of life, about the conditions that produce it, about the probability that chemistry will organize itself into something self-replicating and eventually complex. Every single piece of this knowledge comes from studying a single example. Earth, one world, one outcome. From that one outcome, we cannot reliably determine whether life is common or rare, whether intelligence is an inevitable destination or a contingent accident, whether civilizations tend to destroy themselves or transcend, or simply go silent in ways we do not understand. We are trying to understand the rules of a game by watching it played once. This is not false modesty. It is a genuine epistemological problem. The astrobiologist Caleb Scharf has written thoughtfully about what he calls the N1 problem in the search for life. The fact that every inference we draw about life elsewhere is conditioned on a sample that cannot, by itself, tell us whether its own existence is typical or exceptional. We find ourselves in the peculiar position of being the evidence we are trying to interpret. And here is where the problem deepens. Because Earth is not just our only example of life, it is also, inevitably, a biased example. We exist on this planet. The very fact that we are here to study it means it had to be the kind of planet that could produce us. If Earth were different in ways that made life impossible, there would be no one to notice. This is what philosophers call the anthropic principle. The observation that any universe we find ourselves in must, by definition, be compatible with our existence. The anthropic principle is not a conspiracy or a mystical claim. It is a simple logical constraint, but it means that when we look at Earth and see a planet beautifully suited for life, we cannot straightforwardly conclude that suitable planets are common. We can only conclude that at least one suitable planet exists, because if none did, we would not be here to ask the question. This same logic applies to every feature of our solar system that seems fortunate. The large moon, the protective influence of Jupiter, the stability of our sun, the presence of plate tectonics. We cannot know from the fact of our own existence whether these things are typical or whether we inhabit a genuinely rare configuration. Our survival guarantees that we exist on a world where they occurred. It tells us nothing about how often they occur elsewhere. The uncomfortable implication of this is that the universe might be radically different from what our existence suggests. The conditions that produced us might be extraordinarily unusual, and we would have no way to know it from the inside. Every time we look at Earth and think, this is what a life-bearing planet looks like, we are potentially looking at a lottery winner and inferring that winning the lottery is common. In recent years, the field of astrobiology has undergone a subtle but significant shift. The early days of the search for extraterrestrial intelligence were characterized, in many ways, by a kind of optimism that scientific enthusiasm tends to generate. The numbers seemed large, the galaxy seemed ancient, the conditions for life seemed replicable. The expectation was that contact, when it came, would be a matter of patience rather than luck. That optimism has not disappeared, but it has been tempered by a deeper understanding of how complex the path from chemistry to civilization actually is, and by the persistent, stubborn, unrelenting silence of the sky. A new generation of researchers has begun to take seriously a possibility that earlier generations tended to dismiss as too pessimistic to be worth engaging. The possibility that the silence is not a puzzle waiting to be solved by better technology, but an answer in itself. Not an answer that we are definitively alone. The universe is too large and too old, and our search too limited for that conclusion, but an answer that intelligent, communicating civilizations capable of leaving detectable marks on the galaxy are, at the very least, not common. Perhaps extraordinarily rare, perhaps rare enough that the nearest one, if it exists, is so far away that communication across the distance is not merely difficult, but effectively impossible on any timescale that matters to a civilization with a finite lifespan. Consider the constraints of what we might call communicable distance. The speed of light is the ultimate speed limit imposed by the physics of our universe. A signal traveling at light speed from a star 1,000 light years away takes 1,000 years to reach us. A reply takes another 1,000 years to return. A conversation across that distance would span 2,000 years, minimum. Longer than recorded Western civilization. If the nearest technological civilization is 10,000 light years away, a single exchange of messages would span 20 millennia. If it is 100,000 light years, still well within the Milky Way, a conversation requires 200,000 years, longer than our species has existed. The implications of these numbers are not just practical. They are, in a strange way, existential. Even in a galaxy that contained thousands of civilizations, scattered across its 100,000 light-year diameter, those civilizations might be effectively isolated from one another, not by hostility or indifference, but simply by the geometry of space and the physics of information travel. They would exist in the same galaxy, the way thoughts exist in a vast brain. Real, active, even numerous, but unable to reach each other across the distances between neurons. A civilization that sent a message and waited for a reply might wait longer than it takes stars to form and die. The timescales of interstellar communication do not match the timescales of civilizations. We exist in moments. The universe operates across eons. There is a version of this problem that is rarely discussed, but that carries a peculiar weight Once you begin to think about it carefully, we have assumed throughout this discussion that the question of other civilizations is a question about finding them, detecting their signals, perhaps someday visiting them, or being visited. But there is a prior question that tends to get overlooked. Would we recognize them if we found them? Not a distant civilization, not one sending precisely formatted mathematical sequences in radio waves, not one conveniently announcing itself in ways our instruments are designed to detect, but a civilization that is genuinely different, organized according to principles we do not share, using technologies we have not imagined, pursuing goals that do not map onto anything in our evolutionary history. The biologist J.B.S. Haldane famously remarked that the universe is not only queerer than we suppose, but queerer than we can suppose. This applies with particular force to the question of alien intelligence. Our entire cognitive framework for recognizing intelligence is built on experience with one type of intelligence, our own, and the limited forms of it we observe in other animals on Earth. We recognize intelligence in other creatures when they do things that resemble what we do. When they use tools, form social bonds, solve problems, communicate in structured ways. We extend our recognition to things that feel familiar. But an intelligence that processes information in radically different ways, that pursues radically different goals, that exists at radically different scales of time and space. Such a mind might be invisible to us, not because it is hidden, but because we do not have the conceptual equipment to perceive it. The astronomer Jill Tarter, who spent decades leading the search for extraterrestrial intelligence, has pointed out that we should be careful not to equate the search with a search for intelligence per se, but rather with a search for technology. Technology leaves traces that are, in principle, detectable regardless of the intentions of its creators. Heat signatures, altered stellar spectra, patterns in light that natural processes cannot easily produce. But even technology is only detectable if it operates at scales and in modes our instruments can register. A civilization that has mastered quantum computation and processes information at the level of individual atoms would be, from the outside, remarkably quiet. A civilization that has moved beyond physical infrastructure and exists in some form we currently have no vocabulary for would leave no trace at all in any catalogue we know how to compile. We are searching the sky with tools and concepts, shaped by what we have built so far. Over the past 100 years, in the first moments of our technological existence, we are children looking for adults in a dark house, using a candle. Let us return to the great filter, because there is an aspect of it that tends to get underemphasized in the versions that circulates in popular discussions. The great filter is usually presented as a binary. Either it is behind us, in which case we can breathe a careful sigh of relief, or it is ahead of us, in which case we should be worried. But Robin Hanson's original analysis admits a third possibility that is, in some ways, the strangest of all. What if there is no single great filter? What if the path from chemistry to spacefaring civilization contains not one nearly impossible step, but many steps that are each moderately difficult? Difficult enough that the probability of crossing all of them is, in aggregate, extremely low, but not because any single one is obviously impossible. In this scenario, there is no smoking gun, no single bottleneck that explains the silence. Instead, the silence is the result of a long compounding of modest improbabilities. Getting life started is somewhat unlikely. Getting complex cells is somewhat unlikely. Getting multicellular life is somewhat unlikely. Getting intelligence is somewhat unlikely. Getting technology is somewhat unlikely. Avoiding self-destruction long enough to become a spacefaring presence is somewhat unlikely. Each step perhaps passes through 1 in 1,000 worlds, or 1 in 10,000. Multiply enough 1 in thousands together, and you arrive at the same empty sky. This version of the Great Filter is philosophically subtler than the dramatic single bottleneck version. But it may be more realistic. Evolution on Earth suggests that life found its way to complexity through a long series of transitions, each of which took hundreds of millions of years, and each of which might, under slightly different conditions, have simply not occurred. The compound probability argument does not require any single step to be catastrophically unlikely. It only requires the sequence to be long enough. And the sequence, on Earth, was very long indeed. There is something that has been present throughout this entire discussion, largely unspoken, that deserves to be brought into the open. Embedded in the question of why we may never meet another civilization is a question about what we are, what it means to be the kind of creature that builds telescopes and listens for voices that have not spoken, what it means to be aware of our own existence in a universe that may contain no other awareness like ours. The physicist Brandon Carter, working on the anthropic principle in the 1970s, developed what he called the doomsday argument, a statistical reasoning about the likely position of any given observer in the total sequence of observers that will ever exist. The argument, simplified, goes like this. If we assume we are a randomly selected member of all the humans who will ever live, and if we consider that humanity has existed for roughly 100,000 years and currently numbers about 8 billion people, then we should expect to find ourselves somewhere in the middle of the total distribution of humans, not at the very beginning and not at the very end. This implies that the total number of humans who will ever exist is not astronomically larger than the number who have already existed, which implies, in turn, that humanity will not persist for millions of years into the future. The doomsday argument is controversial, and many philosophers and statisticians have raised serious objections to its reasoning. But it illustrates something important about the way the Fermi Paradox and questions of civilizational longevity are related. If technological civilizations routinely arise and then disappear within a relatively short window, a few thousand years, a few tens of thousands of years, measured against cosmic timescales, then the probability of two such civilizations overlapping in time, being close enough to detect each other, and making contact is very small indeed. Civilizations might be like fireflies in a vast field on a summer night. Each one flickers briefly before going dark, if the field is large enough and the flickers are brief enough. Even a meadow full of fireflies can look dark from the right distance. The question of civilizational longevity connects directly to something that is not often framed as a Fermi paradox problem, but that is, in its deepest structure, exactly that. We have, over the past century, developed the capacity to alter the conditions of our own planet at a global scale. We have accumulated enough nuclear warheads to render significant portions of Earth uninhabitable. We are in the early stages of developing artificial intelligence systems that may, within the lifetimes of people alive today, surpass human cognitive capacity across most domains. We have altered the chemistry of the atmosphere in ways that are changing the climate of the entire planet, and will continue to do so for centuries. None of this is, by itself, a verdict on our future. Human beings have navigated existential crises before. Not of this scale, but crises that seemed, to those living through them, potentially terminal. The Cold War brought the world to the edge of nuclear exchange multiple times. The fact that we are here, discussing the Fermi Paradox, is evidence that the worst outcomes did not occur. But what the Fermi Paradox suggests, in its most unsettling interpretation, is that the transition to global technological power is a filter. Not necessarily a filter that destroys every civilization, but a filter that exerts enormous pressure, and from which many civilizations, perhaps most, do not emerge intact. The development of civilization-scale technology appears to happen on a relatively rapid timescale, within a few thousand years of the development of agriculture, and the development of the specific technologies that create existential risk appears to happen within a few hundred years of the Industrial Revolution. In the context of the time available for civilizational development on a planet with a stable star, this is extraordinarily fast. The window between developing dangerous technologies and either managing them successfully or being destroyed by them may be very narrow. If this is true, then the silence of the galaxy is not mysterious. It is the expected outcome. Civilizations arise briefly in scattered pockets of the cosmos. They reach the threshold of technological capability. Most of them do not successfully cross it, and the ones that do may do so by becoming something so different from what they were at the threshold that they are no longer recognizable to a civilization like ours, still standing at the approach. We may be at the threshold right now. This is worth sitting with for a moment, because it is easy to let it slide by as an abstract proposition about civilizations in general, rather than recognizing it as a statement about us, specifically in this particular decade. The first nuclear weapon was tested in 1945. The structure of DNA was described in 1953. The first satellite was launched in 1957. The first human spaceflight happened in 1961. The internet became publicly accessible in the early 1990s. The first large language models capable of sophisticated reasoning were deployed in the early 2020s. In approximately one human lifetime, the span from 1945 to today, our species went from the first controlled nuclear reaction to systems that can engage in extended reasoning across almost every domain of human knowledge. The pace of technological development is not steady. It appears to be accelerating. What that acceleration produces over the next 100 years, the next 500 years, will determine whether humanity is on the passing side or the failing side of whatever filter may lie ahead. And the Fermi Paradox, read in this light, is not just an astronomical puzzle. It is a warning signal embedded in the structure of the universe. A message written not in radio waves, but in the very silence of the sky. If the galaxy were full of chattering civilizations, we might conclude that the threshold is routinely crossed and the future is open. The silence suggests otherwise. And a universe that appears empty of advanced, persistent civilizations is a universe telling us something about what tends to happen to species like us. Whether we choose to hear that message and what we do with it is the question that follows. There is another dimension to this that has emerged most clearly in recent decades. As the capabilities of computing and artificial intelligence have grown, It concerns what happens to a civilization that successfully passes through the dangerous threshold, that manages its weapons, stabilizes its climate, avoids the failure modes that may have ended others. What does such a civilization become? The philosopher Nick Bostrom and others have speculated about what they call post-human or post-biological civilizations. Species that have transcended their biological origins and exist in forms that are fundamentally different from anything we currently experience as living. A civilization that has existed for 1 million years under conditions of technological expansion would, by almost any reasonable extrapolation, be as different from us as we are from the first self-replicating molecules in the early oceans of Earth. Such a civilization might not exist in biological bodies. It might exist in computational substrates, running simulated environments of unimaginable richness and complexity. It might exist at scales of space and time that are difficult to comprehend. Either vastly larger, if it has spread across stellar systems, or vastly smaller, if it has discovered ways to pack consciousness into structures at the quantum level. And crucially, such a civilization might have no reason whatsoever to announce itself. Not because it is hiding, but because the concept of broadcasting a radio signal into the galaxy might be as quaint to it as smoke signals are to us. Its communication, its activity, its existence might occur at levels completely inaccessible to the tools we currently use to listen. The physicist Freeman Dyson speculated decades ago that an advanced civilization, seeking to maximize its use of stellar energy, might dismantle its home star's planets and reassemble the material into an enormous structure surrounding the star. What has come to be called a Dyson sphere, capturing most of its energy output. Such a structure would be visible in infrared light. Astronomers have actually searched for Dyson spheres among nearby stars. They have not found any, but perhaps that tells us that civilizations do not build Dyson spheres. Or perhaps it tells us that civilizations which survive long enough to build them also transition into forms that no longer need to. Perhaps the most advanced civilizations are, paradoxically, the quietest. Not because they have disappeared, but because they have found ways to exist that produce very little of the kind output our instruments are designed to detect. A universe full of ancient, quiet minds. Each evolved beyond the need to announce itself. Each absorbed in forms of existence we cannot currently imagine, would look, from our vantage point, exactly like an empty universe. There is a concept in the philosophy of mind called the hard problem of consciousness. The question of why physical processes in a brain give rise to subjective experience. Why there is something it is like to be you, reading these words right now, rather than simply information being processed without any inner witness. This problem has resisted every attempt to dissolve it. We can describe the neural correlates of experience. We can map which parts of the brain are active when different thoughts and feelings occur. We can build systems that process information in increasingly sophisticated ways. But we cannot yet explain why any of this is accompanied by experience, by the felt quality of existing, of perceiving, of wondering. The hard problem is relevant to the Fermi Paradox in a way that is rarely made explicit. When we search for extraterrestrial intelligence, we are searching for minds, not merely for information processing systems, for minds. Entities with something like inner experience, something like curiosity, something like the desire to reach beyond themselves and make contact. But we do not know what gives rise to minds. We do not know whether consciousness is a common feature of complex information processing systems in general, or whether it depends on specific biological arrangements that may be rare, or whether it is something else entirely, perhaps a fundamental feature of certain kinds of physical organization that has nothing to do with biology at all. If consciousness is common, if it arises naturally in any sufficiently complex information processing system, then the universe may be far more inhabited than the silence suggests. But much of that inhabitation might be invisible to us, existing in forms of substrate-independent experience that leave no electromagnetic signature. If consciousness is rare, if it depends on specific biological or physical arrangements that occur only under narrow conditions, then we are back to the rare Earth problem, but now at the level of experience rather than mere chemistry. We do not know which of these is true, and that uncertainty is not a temporary gap waiting to be filled by more neuroscience or better philosophy. It runs deep into the nature of what consciousness is and how it relates to the physical world. We are searching for other minds in a universe where we do not yet fully understand what a mind is or why it exists at all. By this point, many threads have been woven together, and it may be worth pausing to notice what they have collectively produced. Not an answer, but a clearer sense of the shape of the question. The Fermi Paradox is not one puzzle. It is several puzzles nested inside each other. There is the puzzle of origins. How easily does life arise from chemistry? And how often does that life find its way to complexity? The evidence from Earth suggests that simple life appears readily, but complex life is the product of an extraordinarily long series of transitions, each of which might not have occurred. There is the puzzle of intelligence. How often does complex life produce the specific kind of cognition that leads to technology and communication? The evolutionary record on Earth suggests that it happened once, in one lineage, under specific conditions that were themselves the product of contingent history. There is the puzzle of survival. How often does a technological civilization navigate the dangerous period of its early development without destroying itself or being permanently destabilized? We do not have an answer to this because we are still in that period ourselves. There is the puzzle of persistence. How long do technological civilizations last, and in what forms do they eventually exist? A civilization that lasts for 1 billion years under conditions of technological mastery would be so different from us that we might not recognize it as a civilization at all. And there is the puzzle of recognition. Even if other minds exist and have existed for billions of years in our galaxy, would we know how to find them? Would they use the channels we monitor? Would they exist at scales our instruments can probe? Would they be looking for us? Each of these puzzles has multiple possible answers. The correct answer to each is currently unknown, and the combination of those unknown answers is what determines whether the universe is full or empty of other minds. What we can say, standing where we stand today, is that the silence is real. The sky, by every measure we have applied to it over decades of careful searching, is quiet. And that quiet is, depending on how you approach it, either a testament to our extraordinary rarity or a warning about what lies ahead, or both simultaneously. There is one final aspect of this question that deserves to be examined before this exploration comes to rest. It concerns not the universe, but us. What the Fermi Paradox asks of us, not as scientists or philosophers, but as a civilization at a particular and peculiar moment. We exist in the first era of our species' history, in which the question of other civilizations can be approached scientifically, rather than mythologically. For most of human existence, the question of other minds in the cosmos was answered by religion, by tradition, by the particular cosmology of whatever culture a person happened to be born into. The heavens were populated by gods, by angels, by spirits, not by other technological civilizations, but by other kinds of being that were different in kind from us, not just in scale. The scientific version of the question is new. It is less than a century old in any rigorous form, and it has already changed the way at least some people understand our position in the universe. That repositioning is not comfortable. The old cosmologies, whatever their other features, placed human beings at or near the center of a universe that was, in some sense, organized around us. The universe of modern astronomy places us in a very different position, a small planet orbiting an ordinary star in the outer reaches of one galaxy, among hundreds of billions, in a universe that has existed for most of its history without us, and will continue to exist for most of its future without us. The Fermi Paradox adds another layer to this repositioning. It suggests that even within this vast universe, we may be profoundly alone, not just small and peripheral, but rare in the way that matters most. Alone not in the way a person is alone in an empty room, but in the way that awareness itself might be alone in a cosmos that produces it only occasionally, only briefly, and with no guarantee of continuation. That is a weight, and it is honest to acknowledge it as such. But there is another way to read the same situation. If the universe is in fact largely empty of minds, if intelligence and awareness and the capacity for wonder are genuinely rare across cosmic scales, then what exists here is not diminished by the emptiness. It is perhaps more remarkable for it. A universe in which every star shelters a civilization makes any particular civilization less extraordinary. A universe in which minds are rare makes each mind more precious than any number of stars, because stars will burn regardless. Minds, awareness, curiosity, the capacity to ask where everyone else is. These require conditions and histories and improbable sequences of events that the universe does not distribute casually. We may be, not in spite of the silence, but in some strange way because of it, among the most extraordinary things the universe has produced. The search continues. It will continue, not because we are certain that something is out there waiting to be found, but because the question is too important to abandon, and because the history of science is a history of finding, again and again, that the universe is stranger and more populated with wonders than previous generations expected. We have discovered, in the past 30 years alone, that virtually every star in the galaxy is accompanied by planets. We have discovered water ice on the Moon and on Mars. We have discovered complex organic molecules floating freely in interstellar space. We have discovered that the subsurface oceans of moons like Europa and Enceladus represent environments where liquid water exists in contact with rocky seafloors. Conditions that, on Earth, sustain thriving ecosystems in the complete absence of sunlight. The James Space Telescope has already begun analyzing the atmospheres of exoplanets, looking for the chemical signatures that might indicate biological processes. Future telescopes, still in the planning stages, will be capable of detecting biosignatures. The presence of gases like oxygen or methane in combinations that nature, without biology, does not easily produce on worlds orbiting distant stars. These searches might find nothing, or they might find something that changes everything. The discovery of even the simplest microbial life on another world would be the most significant event in the history of science, and it would dramatically change the terms of every conversation this documentary has attempted to have. It would tell us that the origin of life is not the filter, and redirect our anxiety toward what comes after. We do not know what we will find. That uncertainty is not a failure. It is the condition of a young civilization at the very beginning of its exploration of the universe it inhabits. Near the end of its long journey outward from the sun, as it crossed the outermost boundary of the solar system's influence and entered the true interstellar void, the Voyager 1 spacecraft turned its camera back toward home at the request of the astronomer Carl Sagan. The resulting image showed Earth as a tiny point of light, suspended in a beam of scattered sunlight. A pale blue dot, barely distinguishable from the background of space. Sagan wrote about that image that it underscored the responsibility we bear toward one another and the loneliness of our place in the cosmos. That every human who ever lived, every king and peasant, every inventor and conqueror, every moment of love and cruelty and discovery and loss had occurred on that barely visible point of light. What the Fermi Paradox adds to that image is a further dimension of solitude. That dot may be not just our home, but the only place in a very large volume of space where anything is aware of the image at all. The only place where the light has been gathered and focused into an eye that can see it and a mind that can wonder at it. Perhaps that will change. Perhaps the next century of searching will reveal that the silencer is a failure of our instruments rather than a feature of the universe. Perhaps we will detect a signal, find a biosignature, discover an artifact, something that tells us the cosmic loneliness is an illusion born of limited search. Or perhaps the silence will deepen. Perhaps future searches, more sensitive and more comprehensive than anything we have attempted, will confirm that the emptiness is real, that the galaxy is not teeming but sparse, that we are what the mathematics of improbability occasionally produces but does not reliably repeat. Either outcome would be extraordinary. Either outcome would be worth knowing. The question Fermi asked over lunch, "Where is everybody?" has no clean answer. The silence that prompted it has no simple explanation. But what the decades of thinking that have followed that question have produced is something valuable even without a resolution. They have produced a clearer understanding of how improbable our own existence is, not in a way that makes existence feel like an accident to be dismissed, but in a way that makes it feel like something earned. Through billions of years of chemistry and evolution and contingent history, and, eventually, the peculiar emergence of creatures capable of standing on a pale blue dot and asking whether anyone else is standing somewhere similarly, looking up at the same universe from a different vantage point. They have produced an honest accounting of the risks we carry, the same technological capability that allows us to build radio telescopes and launch spacecraft and decode the chemistry of distant worlds, also gives us the power to alter our planet's climate, to release engineered pathogens, to build weapons that could end civilization as we know it. The Great Filter hypothesis is not a comfortable idea, but it is a serious one, and its seriousness demands that we take our own fragility seriously. and they have produced a different kind of relationship with the cosmos. Not the relationship of creatures who believe themselves to be at the center of a universe designed for them, but the relationship of creatures who understand that the universe did not design itself for anyone, that its great age and indifference are real, and that awareness of that indifference is itself the most extraordinary thing we know of. The silence of the universe does not tell us that we are alone. It cannot tell us that. The universe is too large, and our search too new, and our instruments too limited for certainty in any direction. What the silence tells us is something subtler and more demanding. It tells us that intelligence, this strange, briefly burning capacity to understand, to wonder, to reach, is not something the universe produces casually. It tells us that whatever produced it here on this world was the result of a long and improbable journey that might not have ended the same way under almost any other set of conditions. It tells us that if other minds exist, they are not nearby and not obvious and not calling out to us in ways we have yet learned to hear. And it tells us that what we are and what we might yet become is not guaranteed. That civilizations can fall silent for reasons we may be in the early stages of understanding. That the silence of the cosmos might be, among other things, a record of failure, of worlds where the chemistry worked and the evolution proceeded and the intelligence arose, and then something went wrong. We do not have to be part of that record. The Fermi Paradox is not, at its deepest level, a question about aliens. It is a question about us, about what we do with the awareness we have developed in this brief window of cosmic time, on this improbable planet, in this ordinary corner of an extraordinary universe that may or may not contain anyone else looking back at us. The sky is quiet. What we choose to do in the silence is ours to decide.